Welcome everybody on Zoom, welcome everybody in the lecture hall. So today we are going to spend almost all our time on JSONic to query denormalized data. You know by now that data is denormalized in different ways, and mostly because it's nested, tables in tables in tables, and because it's heterogeneous, meaning that you can have extra fields, missing fields, or fields with different types in the same column, right? So I have a few questions that I would like to ask you first, before we start. Let's start here. Which of the following adjectives, of course, which of the following adjectives characterize a well-designed query language? Functional, imperative, low-level, declarative. Functional, imperative, low-level, declarative. Multiple answers are possible. Answers are still coming in. Let's see what you've said. And indeed, we have the big two, which are functional and declarative, right? So what do they mean? Declarative means that you don't specify the details of how things are going to get computed. You just say what you want, a selection, a projection, and so on. The details, whether it's in parallel, it's materialized, streaming, and so on, is basically left to the execution engine. In fact, this is the reason why last time, so you asked a lot of questions that were actually on the physical level, the implementation, right? But the idea of a declarative language is that when you write the actual query, you don't actually worry too much about the way that it's implemented, right? It should just work normally. Of course, it's true to some extent, right? So some knowledge is actually still useful to understand what's going on. Functional means that you can think of the language as basically plenty of function calls recursively calling each other. But functional does not mean that you actually have syntactic function calls in the syntax, because that would be ugly and not very productive, right? You would have parentheses everywhere. So rather, even though it's functional, typically syntactically, what you have is expressions that nest with each other. And the way it's done is what you saw with context-free grammars in theoretical computer science, right? You typically design the grammar of a language in such a way that you nest expressions in each other. Imperative, no, not at the query language level. What would be imperative is the implementation of the engine, right? So RumbleDB, for example, is implemented in Java, and this is all imperative, right? But the whole point is that whoever programmed it imperatively, and here I'm thinking of the 20 students who worked on it so far, they did it so that you don't have to do it anymore, because all you need to do then is to write in the functional language. A low level is also not true. The whole point of a query language is to be at a high level, right? So the low level would be, in the case of RumbleDB, that would be Java, the RDD, the Spark RDD API, the Spark data frames, all of that is low level compared to the query language. All right, here's another question for you. Why should it be functional and declarative? So that queries can be parallelized, so that an optimizer can make the query faster than it would have been with the literal execution of the user's query, in order to delegate the details of the execution of the query to a machine rather than doing it yourself, or because queries are more concise and easier to read and understand. Multiple answers possible. You don't like the first answer? Ah, some of you do. Okay, well, in fact, everything is correct. All of that is jointly correct. This is why all the benefits of having a functional and declarative language. You can parallelize, you can optimize, you can delegate the details of the executions, you can have execution plans with cost computations to pick the cheapest one. And it's concise, it's easier to read, there are less parentheses and chains of function calls than you would have in APIs, right? Finally, what does the JSONic data model process? Is it relational table? Is it trees exposed as maps and arrays? Is it sequences of items or only single atomic values with a rich type system? The JSONic data model. So this is basically what every single expression in JSONic takes and returns. Ah, almost. Can change your mind? No? All right. It's sequences of items. Sequences of items is whatever comes out and into expressions in JSONic. What are items? Objects, arrays, atomic items. This is why the second answer is not correct, because you can also have atomics in the mix. You have the rich type system. So the fourth answer is incorrect because you can also have objects and arrays. Relational tables, that's a subset of what you can do with sequences of items, right? It's a special case. A relational table is just a sequence of objects that are valid against the same schema, right? That's a relational table. So these are sequences of items. In fact, we've seen sequences of items way before, right? Whenever we looked at collections of key value pairs, you can see them as sequences of items in MapReduce. The very large files with plenty of lines, you can see them as sequence of string items. In Spark, RDDs are also sequences of items because RDDs can be of anything. And in JSONic, these are sequences of items. So the terminology sequences of item is part of the W3C standards. All right, and again, they can be heterogeneous, the sequences of items. All right, so that should be an automatic thought. You process sequences of items. Everything that comes in and out of an expression is a sequence of items. Okay, so now I'm switching back to the slides. Now we can continue. So we are going to use a lot these data sets, the GitHub archive, also very popular with the exam because it's a bit heterogeneous and that wouldn't fit in a relational table, except if you put a lot of nulls and have variant types for the heterogeneity. And the idea, just as a reminder, is that we have an implementation of the JSONic language, which is the logical level, but it's implemented thanks to Java on top of Spark, and it can query from HBase, HDFS, and so on and so on. Okay, so that's RumbleDB. And now again, what's very, very, very important to understand, everything is a sequence of items, but there's plenty of ways you can have sequences of items. You can have, of course, the messy sequences of items that are just sequences of anything. So you can have in the same sequence, right? An integer, then a Boolean, then an object, then an array. This is just a huge mess, right? And then you can have more structured sequences of items. You can have sequences of arrays. You can have sequences of objects. That would actually be a relational table, right? That's where you recognize probably the pattern. You can also have sequences of atomic values, sequences of Boolean, sequences of integers. The special case of a single item, which actually is very often as well. This is, of course, more efficient, as we will see a single string in that case, or the empty sequence, right? The empty sequence is not the same as null, right? It's just a sequence that has no items at all, right? So you see, it's the whole spectrum from unstructured to structured. And RumbleDB is very good at executing these ones very, very fast and efficiently. And then it gracefully deteriorates in performance, but can still deal with these heterogeneous sequences. This is where the relational systems would break, basically, or a Spark SQL and so on. All right. Okay, so let's now start maybe with the most useful part, probably that that there is in querying large data sets. One thing that sometimes you want to do if you're given a large data set is discover it. You want to explore it and start understanding what there is in there, right? And for this, you have a navigation syntax that should be a bit familiar because it's similar a bit to JavaScript with the point for object lookup and so on. So imagine that I have here, I took the example of a JSON document. So it's not JSON lines here. It's really a single JSON document file, small, with a single JSON object in there. So this is what JSON doc does. And JSON doc returns what? A sequence of items, always a sequence of items. But in that case, it's a sequence of one object. That is what you see on the right. Now, if I say .country, what's happening is that it navigates down to the value associated with countries, which is also a sequence of items. But in that case, that item is one array. It's a sequence of one array. Who is following? All right. Now, let's do something interesting. Let's go into the array with this double square bracket syntax. It's called unboxing. So now I open like a Christmas present. I open the array, and now I get a sequence of how many items? 5, exactly. Now the 5 objects that were inside the array, they pop up out of the array. Now we have a sequence of 5 items. This is what this query returns, a sequence of 5 objects in that case. Note that in fact, this is a relational table logically, right? Because that's basically a table with 2 columns, name and code, and 5 rows. Who sees that? Right. So as you can imagine, this is very efficient to implement because that can be done actually inside as a table or data frame.
There's a question.
Yes, over there. Yes, maybe that's a bit far away. Let's try. Maybe 2 hops, 1 hop and a second hop. There you go.
Yeah. Yeah. So, so you said countries would give you a sequence of like object, but then what if there were multiple? I mean, now it's one. So then when you do .countries of one box, like, is it a flat map or just a map or like?
It's flat, a flat map.
Okay.
Look at this. Maybe this will help you, right? If I add now .name after my array unboxing, .name is going to go into each one of the 5 objects, and it's going to return the 5 strings in there. It's always a flat map in the sense that everything is always flattened. Sequences are always flat no matter what, right? The only way you wouldn't have something flat is if you box it into arrays, right? But that you need to do explicitly, or you would actually have an array. If you don't have arrays, this is always completely flat, right? So for example, if you had here, we only have 1 array of objects, but imagine that you have an array of objects, and inside there is again arrays of objects. Then if you do square brackets .foo square brackets .bar, again, it's flattened all over the place. So every time you get the flat sequence of all the objects. It's extremely powerful to quickly navigate through billions of items like that. Right? So you can just go inside with dots and square bracket, and you could do it again. This must be a question multiple times, arrays in objects, in arrays in objects, in arrays in objects. You can always go down, down, down. It always flattens everything. Right? Does it answer your question? Awesome. All right. So this is .name, which outputs a sequence of 5 strings. Right? These are items, right? These are 5 strings. And this is also 5 strings, right? A sequence of 5 strings. So now you probably understand the logic that dots work in parallel, and the square brackets would also work in parallel. So if there was even nested arrays, you would also open them and then flatten everything. So it would be the concatenation of their contents. Now something new. That's called the predicate. It's a little bit like the where clause in SQL, even though it also exists in JSONic. This is a quick way of filtering things. So if I just take this here, just these 5 objects, imagine that I want to select some of them that satisfy a criterion. Maybe my criterion is that the code must be CH, right? I'm looking for Switzerland. So what I do is that I put with these single square brackets a predicate, a Boolean predicate that is testing whether the current items .code equals CH. This $$ that you see here is the current items. it's going to be bound in turn to each one of the 5 objects. So first you test this code, is it CH, that's true. Then $code, is it CH, that's false, because F is not CH. Then $code equals CH here, that's false. $code equals CH, that's false. $code equals CH. So you see, this $$ takes in turn one item at a time, right? What's here returns potentially several items on the left-hand side. This $, one item at a time. That's called the context item, this $. So every time you check this predicate on every single item, and if it's true, you keep it, right? So here, the only objects that we had that satisfies this criterion is this one here. So that's now a sequence of one single object. And you can even continue. You see, it's all composable. .name would be Switzerland. So that would be a query that looks for the name of the country with the code CH, and it returns Switzerland. In that case, it's a sequence of one string. Who is following? Who would feel now comfortable navigating like that, big data sets? Okay, very good. Now what you should know is that in that case, it's homogeneous. What if it's heterogeneous? It will still work. What's going to happen if you try a countries, sorry, maybe on several of them, on .name on plenty of items, what is not an object is just thrown away. It's ignored. So it's just going to do the .name on the objects, and it ignores the arrays and the atomic values and so on, right? And the objects that don't have it, it ignores as well. So it's not going to throw any errors. It's just going inside the objects in the sequence. The same goes for these brackets. If you have a sequence on the left, so this .country here, it turns out to be a sequence of arrays, a sequence of one array in that case. But if you have something else than arrays, they are ignored. So if you have a sequence with objects and arrays and atomic items, objects and atomic items are ignored, and the arrays are unboxed. So you see, even if you have a very, very messy and heterogeneous data set, it will still work. Okay, for whom is that clear? All right, so these are things that you do not get with data frames or a Spark SQL. All right. Now, so this was JSON doc. This is to do small things on your laptop, right? Nothing fancy. It's just a file on your laptop. You can also now open this JSON lines file. Remember, these are these files that can have billions or trillions of JSON objects, one per line, and we store them in HDFS, in S3, in Azure Blob Storage, no matter where you want, maybe even in multiple files. This is what we call shards, right? You can even maybe have 1,000 files in a directory, and you explore them. So now we use JSON-file instead of JSON-doc. JSON-doc would be a multi-line JSON documents. JSON file is this JSON lines format. So now it's countries.json. So imagine that I have probably 200 of them roughly. It's still small, right? 200, but this is just to make my point. And now I go through that file. JSON file now doesn't return a single object as JSON-doc was doing, right? JSON-doc was just returning one object. JSON files returns a flat sequence of JSON objects, all of those that belong to that JSON lines file. So how many items are returned by JSON file? 5 of them in that case, 200 if you had the complete list of countries. And then you filter these objects with these predicates. $, is going to be bound in turn with each one of the 200 countries. And then it's only filtering the CH here, based on code CH, and then returning the name. So this query would return Switzerland, even on 200 countries. Who understands that? To whom is that natural? Okay, very good. So this was a bit of the appetizer of navigation. So what if we do it on the GitHub archive dataset? It turns out that if you go to either rumbledb.org or jsonic.org, you can click on the top right for a tutorial. You can also, if you prefer, execute it on your own computer, but there is also a public sandbox with super tiny machines of just 1 GB of memory and 1 core. So be kind to them, even though they restart every day. But you can play around with that. Do we have a question in the Zoom chat?
Can a single JSON object span over multiple lines, or are there new lines treated as delimiters?
Yes, in the case of a JSON document file. So you do have JSON document file where you can have a gigantic JSON object, maybe on 200 lines that has plenty of nested structure, but it's still a single JSON object on multiple lines. This is the JSON format. That would be the actual raw JSON format, which is not to be confused with the JSON lines format, which is different, which here has one object per line, and here the new lines are important, right? Because these are the new lines that delineates the objects. Why is it so important, this JSON lines format? Because this actually scales to billions or trillions. You can actually have that on HDFS or S3 with trillions of lines, it will work. This here, having an enormous JSON file with maybe an array, where is it here? Imagine a gigantic file that is 1 terabyte and it has a single object with one array that has 1 million or 1 billion objects in there. Of course, logically, it works. You could navigate it. You could have 1 billion countries if you wanted to, all of those in the Milky Way. But the problem is, this is very, very hard to actually implement. If you need to actually partition something like that, this is very challenging. Maybe some of you will figure out a way to do that, but this is why it's not done that way. And instead, when we actually have billions of objects, instead of putting them in an enormous array, we prefer to put them without any structure once per line, like this. So this is a very common pattern. Did I answer your question on Zoom? Right, so distinguish on the one hand JSON doc for multi-line documents with a single JSON value, and on the other hand, the JSON lines files that have one object per line. Of course, as big data, I love JSON lines because this is how I get my trillions of objects.
I guess there's a second question, but here.
Yes?
Wondering, does this support any indexing or slicing? For instance, if I want to get the first item or like the 5th to the 10th item.
So it depends if the implementation of JSONic is a data lake or a proprietary system. If it's a data lake, as is the case with RumbleDB, then you don't have indices, right? You would do a full scan to find it. But JSONic also works very well on document stores. You could have JSONic on top of MongoDB, on top of Couchbase and, you know, Elasticsearch. That works very well. And then you have indexing. And then you can implement JSONic in such a way that it's going to use the indices, and be very fast, right? So thank you for asking this. So again, JSONic works for data lakes using Spark and GFS, as well as on document stores. But in our case, we are going to focus on data lakes right here. Okay. Okay, so now I'm taking a file gitarchive.json. This URL actually exists. It would actually work if you exactly type this, and you can pass an HTTP URL in JSON file, it will work. It's going to take it over the web, from the web. Of course, as you imagine, if you take it from the web, it's not going to download trillions of them, right? You would have to use HDFS or S3 for that. So be careful if you use HTTP, it's really going to be a single download without any parallelization. Okay, it might spread it over the cores once it's downloaded, but it's still downloading a single file. Okay. So this here is just JSON file of gitarchive.json that is a subset of the entire data set. And you can see there's actually 36,577. That would be on the shell, on the command line, that it looks like that. And you press twice return and then get the results. So here I just showed one of them. By default, it's showing the first 200 items. And then there's this warning that says, beware, beware. There's actually more than that, but it's not going to overload your screen with all of them. If you don't like 200, you can change the value of 200 to something else, of course, right? Okay, now if I, yes?
There's the question here.
Yes, go ahead.
Quick question related to JSON lines and JSON documents. So saying that we would, so in the case that we have a very big JSON document, for example, like you said, we have an array that has a lot of objects in it. We would first then use JSONic to split it into JSON lines and then continue to process it as JSON lines, or how we would get it to JSON lines from that big JSON?
So the way I would formulate it is that you shouldn't create that sort of data set in the first place. So whoever created a data set with an array with 1 million objects probably didn't think through of the consequences for the users. But of course, you might actually have data sets like that have these sort of issues. Then you probably need to take the biggest machine there is on Amazon, open this, and then store it back, like take the sequence with the navigation. You can do it with RumbleDB and output it back to JSON line files, right? And then you can go ahead and use that JSON lines files, right? But here, what this is related to is really data preparation. When you put a data set over the internet for people to use, you have to be kind of big data ready. So you are doing people a favor if you have millions of items or billions of items. If you put one per line, you will make it easier for them to open it, right? Thank you. All right. Okay. what is this square one? Well, this takes the first object. So you don't have to have a Boolean thing in there. We saw a predicate earlier with code equals ch, but you can also put a number, and then that takes the one at that position. So one, we start counting with one with JSONX. So this is the first one, the first object only. If you put two, it's going to be the second one, and so on. All right. So this is to explore, right? If you have a big data set, probably this is what you want to do. Let's look at the first one. So you can do that and just show the first one on your screen. Then you could also say, okay, what are the keys? You know, you don't know the data set, you're exploring, what are the keys? Just call JSON file and then wrap it in a keys function call. And in that case, you see that there's 1, 2, 3, 4, 5, 6, 7, 8 keys, right? It's eliminating duplicates. So basically what you're looking at is kind of a table with 8 columns, if you want. Maybe it might be sparse, maybe it's heterogeneous and so on, but it kind of has 8 columns. So you see, you can learn things about an unknown data set, right? All right. But of course, you could also have thousands of keys. Maybe you don't know in advance, right? Then what you can do to explore, instead of looking at the keys, you can take one of the keys. So let's take this key right there, type here, and let's try to explore dot type. So now you know this works on the entire sequence, right? For each object is going to go to type. And what we see is that these are all strings. So type is associated with a string. But now, of course, there are as many strings as the number of objects. Here we were lucky. It was actually homogeneous. There seems to be only strings. Or maybe there's, you know, non-strings somewhere, we don't know, but we only see the first ones. But now you see there's duplicates because I didn't eliminate any duplicates, right? I just blindly return whatever there is. So the first object has push events, the second one has push event, and so on. All right. So what I can do is call distinct values here. That's a function. There's a lot of functions that are actually very useful. Distinct values takes a sequence of atomic items and it eliminates the duplicates. So what we get here is the distinct values for the field type. So you see there's 1, 2, 3, 4, 8, 9, 14 roughly. I'm not sure if I'm counting it well, but roughly 14 different types. This is the sort of things you do when you discover a data set. You do schema discovery and then you learn about it, right? You could also try, let's see, created at, for example. That's another one of the keys that there was here, right? Created at below type. So we can go there and count the number of distinct values, still exploring the data set. So here we learn that there are 3,597 different values for created at for this data set. Okay. Now I can also count the entire collection, right? So I can just do count JSON file. This is going to be efficient. If you're trying to read from HDFS, it's not even going to bother parsing the JSON. It's just counting the number of lines. This is all pushed down very efficiently, right? So a count is actually relatively fast, actually. Faster than displaying the entire contents. Okay, now, of course, you can go for bigger data sets. So what is recommended when you do that sort of things is to start small. So Git archive is a quite small subset with 30K plus objects. Then there is a bigger one that has 200. I think this is an entire hour of data, this one on GitHub. So here you have 206, 978. If you are courageous, and maybe you can do it on the Azure cloud when it's ready, so the TAs are working on it, you can actually download all the data sets for every hour there is a file in the previous year. So you can imagine the size of the data, it's absolutely gigantic. If you manage an entire day, that's good. Maybe an entire week, who knows, an entire month, if you're lucky. Probably if you want to go all the way to you know, the very early days of GitHub, that might be more costly in terms of clusters. So we probably cannot support these costs, but this is a good thing to explore, right? So you can download. So you see this is sharded in that case, because we have separate files. What is this GZ? It's a compression. This is actually compressed, but it turns out that you can directly open the compressed file. It's automatically going to take care of decompressing it for you, right? This is also quite useful because decompressing would take time otherwise. So it does it on the fly. So you just do JSON file. You can use the star, the asterisks to take all of them, star.json.gz, it's opening all of them. And in that case, that's how I managed to push it. I spend maybe half an hour trying to get as big as I can. And in that case, I have how much? 2,013,200,000 items, right? So 2 billion in that case, right? I can't remember, did I do it on my own laptop? I think I did it on my laptop. I didn't even use a cluster for that. With a cluster, you can go even beyond that. All right. But I think it took me 5 or 10 minutes to do the counts when I did it. All right. Who is following? Okay. So you see, you can play on various sizes and you'll have the opportunity in the exercises. All right. So now you can also filter with a predicate on very large sequences. So if you're ambitious, you can use a big one, and then $.type equals push events. That's going to filter for those objects where the type is push event. You see, push event was one of the values, right? How did I find push event? That's because I did this distinct values type and I just picked one of them. So I just picked this one, and knowing that it exists, then I tried to filter for it there. So you see the reasoning, the pattern of the schema discovery and trying to analyze the data set. And you can do that with RumbleDB without knowing anything about the data set in the first place. This is really just exploration. All right, so now let's take a break from these examples. I have more to follow. Let's take a bit of a break here on features of the JSONic language, little parenthesis. It's like a Lego game. I already warned you about that. How do you construct items? Well, it's super easy. Constructing a string, just declaratively write the string, copy paste the JSON string. So this is a sequence of one item. This is a JSONic query that returns a sequence of one items, one string foo. These are other examples to see that you can use the backslashes exactly like the JSON syntax. You can literally take any JSON and copy paste it, and this is going to be JSONic, right? So you can use the Unicode codes and so on and so on. Okay. These are also 3 different JSONic queries that return numbers. And again, that's the number syntax of JSON. What it's going to do is that it has a rich type system. So unlike JSON that just has numbers, in JSONic, it's going to create an integer. Here it's going to create a decimal, and here it's going to create a double, right? And of course, then you can play around, you can cast if you want, but basically it's going to automatically pick the correct dynamic types, the dynamic type that makes sense depending on what you do, right? Okay. All right, Boolean true, false. Again, that's copy paste from JSON. If you write true or false, these are items that are the Boolean true and the Boolean false. How do you do the others that are not JSON literals? Just cast. Casting is done like a function call. You just specify the type that you want, long, in, short, byte, non-negative integer, whatever you want. And here you can put any atomic item, can be a string, can be maybe a number that is a double and that you want to cast to a decimal or whatever. Just put it in there. Or you can put a string if you want to cast from a string, and that's it. It's going to create an item that has the type that you desire, right? How do I know which types to pick? Which types? You already know them. I already gave you the lists many times. I gave you a list in the data modeling lecture and so on. These are exactly the same types as in JSON and XML schema. So there is no new invention here. These are just exactly the same types. Okay, and users can also define their own types if they want, right? If you want to have your own type, like shoe size is the textbook example of a user-defined type, right? Okay, date, time, time. So you see all of these literals, you can actually cast strings that might come from a JSON data set. You can cast it to a date. Here, that would be a date time. Here, that would be a time. And here, a timestamp. Z is for the UTC time zone. So if you have a Z at the end, just says UTC, right? Okay, who is following? Right, so these are just casts as you see them, but of course it's very simple to actually do this sort of cast. These are even more casts. So here you have a type for years, you have a type for months, you have a type for year month. So this says November 2019. You have a type for month day that basically says here November 26 in the time zone of actually that would be the summertime of Europe, but now that would be maybe more to the east. And the day, that would be the 26th of some month. So you see, you have all of this type. It's a very long list. Probably these you won't use so often, right? But these might be a bit more often. Okay, and you have durations as well. I already showed that to you with the P that has the literal of duration. So 1 day, 2 hours, and you have 1 year, 2 months, and then you have 1 year, 3 months, and 3 days, right? Okay, and binaries, you can have binary things. So in base 16, that's called the hex binary for hexadecimal. Just pass a string that contains hexadecimal digits. Or base 64, which you might know it's used over the web a lot to put images in HTML pages. So this is just a base 64 encoding actually base 64 is just like base 16 and base 64, right? It's really literally a base 64 encoding where these are digits of the base 64. Okay. Okay, so what do you do then? You can also construct objects and arrays, and again, you copy paste JSON. It's really that simple. Copy paste JSON in there. This is a JSON query that returns a sequence of one array item. Okay. This here is a heterogeneous sequence. How did I do that? I use commas. So if I put commas, I'm building a sequence. So this is a sequence of 4 items. There is one array followed by a Boolean, followed by a string, followed by an object. This you cannot do with data frames or with Spark. Okay. Then you can also build ranges. So imagine you want a sequence of 100 integers from 1 to 100. Just use the keyword 2, 1 to 100. So it's very convenient with the 4 loops that we'll see a bit later as part of the select from where like expressions, right? This is just a sequence of 100 items, right? So now you know how to construct atomic items, objects, arrays. You can copy paste from JSON. You know how to cast to other types and so on. Then there's the usual that you have in any programming language. There's arithmetics, comparison, logic. So your computer scientist, this is going to be very easy. I just need to give you on the high level how that works. So the one thing to know is that in the language, division is not done with a slash, but with div. IDiv is for integer division and mod for taking the modulo. Right? So this is the syntax. Why not the slash? Is because the slash is used for something else for navigation, but I'm not going to bother you with that. Right? So this is arithmetics, works like any language. What you need to know is that, of course, in other languages, you manipulate one value at a time. In Java, in Python, in C++, you always have one value. But here we have sequences of items. So what if the sequences are empty? What if the sequences have more than one item? So here it goes. Imagine you want to use arithmetics with the empty sequence, what is going to return the empty sequence. So the empty sequence plus 1 returns the empty sequence. Do we have a question on Zoom?
Yeah. Does mod implement through modulo or C++ style modulo?
Oh, that's an advanced question. Maybe, can you explain the difference? Maybe I have to take this offline. What is the difference between these modulos? Is it about the negative numbers or?
Yeah.
Oh, the negative numbers. Oh, I can't remember. I'll come back to you. It's defined. It's basically exactly what the W3C standard says. I don't know it for the top of my mind. Can you please make a note? Then I'll get back to you and tell you which way it is. Because you know that for modulos, you have 2 ways of defining them for the negative numbers. Okay, thank you for asking. All right, so if you try an addition with the empty sequence, that returns the empty sequence. If you try the addition with something that's not a number, then that returns an error. What's funny is that, what's funny or fun, is that you can also add with a plus a date and a duration. You can do November 29th as a date plus a duration of 2 days that's going to return the date of December 1st. And that is awesome. That's the sort of things that in most languages is quite complicated to do. But here, all you do is cast to a date, cast to a duration, and use plus is going to add the duration to the date. This is very, very convenient. Okay, what if there's more than one item? Error, right? You cannot have more than one item. If you add, you really, really have to have one item or the empty sequence, and you return the empty sequence. Okay. You can also work with strings, but here it's almost boring because it's like in many languages, you just use functions, right? So there is a function to join strings, a function to concatenate, or there's also the double vertical bar, like in SQL. You can take the substring, the string length. Yeah, I don't think I need to say much. You've seen so many of these in many languages. So this is just like in many other languages with plenty of functions. Comparison. If you compare one item with one item, you need to use this EQ for equal, NE for non-equal, greater than GT, greater or equal GE, LT lower than, LE lower or equal. So you have these 6 operators. It's a bit similar to MongoDB. In MongoDB, they're called slightly differently. I think it's LTE or something like that. Here it's always 2 letters, right? So this is how you compare single values, all right? And so then it's just like in any other language. Is there also a question? Would using plus on sequences? Is it a joke? Go ahead.
Would using plus on sequences of same length work if their length is greater than 1?
If the length is greater than 1, there's an error. Right? You cannot use plus on sequences that have more than one item. There must be at most one item on the left and at most one item on the right. Did it answer the question?
Yep.
Yeah. All right. All right. So here you go. You see, you can use equality, non-equality that works on strings. You can also use comparison on strings. Actually, it's just the lexicographic order, right? So the only thing we need to remember here is that it's GT instead of the symbol greater than and so on and so on. EQ instead of the equal sign. Why? Because, oh, sorry, it's coming next. I will show you why we are not using the symbols because they are used for something else. Now, this is easy to remember. It's like plus. If you try to compare an empty sequence with another item, then that's going to be the empty sequence, right? So this is just as for plus. So very easy to remember. If you try to compare a string to a number, again, that's an error. This is different from MongoDB, right? In MongoDB, you could always compare cross types, but here that's an error. Now, why are we using EQ, LT, LE, and so on? This is because if you use equal, the actual signs that you find usually in languages, they have superpowers. They have superpowers because they actually work on sequences. And what they are doing is, if I want to sound fancy, it's an existential quantification on the sequences. Meaning that if you have two sequences of any size and you use equal, it's returning true if there exists one item on the left and one item on the right that are equal, as with EQ, right? So if you have two items that are equal, then it's returning true. And it's going to return false if there is no intersection. There are no two items on the two sides that would be equal. So here, that returns true because you have one that is on both sides. For whom is that clear? Right. The same goes for the others. Greater than, lower than, and so on. If you use the actual sign, it's going to return true if there is at least two items. So here it returns true, for example, because 1 is smaller than 3, right? So this is why it's extremely powerful. This returns false because you never have any item on the left that would be greater than or equal to any item on the right. Who agrees that it's false? Okay, most of you. Yes, we have a question over there. Catch box.
Could you repeat the less than case? I didn't understand it.
Yeah, this is an existential quantification. So it's returning true if there exists an A on the left and a B on the right, such that A is lower than B. This is what it means. So here we have, as an example, 1 lower than 3. That's one example of that. So this is true. We could also have said 3 lower than 4 or anything like that. But in that case, it's true. And this is here an example where it's false, because here you can try all you want to find an item on the left that would be greater than or equal than an item on the right doesn't exist, right? So as you can imagine, this you can do lazily in implementation. As soon as you find 2, that's it, you're done. You don't even need to look at the rest. But if it's false, you have no other choice than to look at everything. There is no way you can say false unless you have looked at the entire sequences. For whom is that clear? Okay. This is an error. You cannot compare two strings, so that would actually throw an error. And so on. So this is very convenient for that kind of use cases. For example, imagine you have a sequence of strings that you obtain from a dataset .name that gives you a sequence of strings, right? .name gives you Switzerland, France, Germany, so 5 strings there. Then you do equal Switzerland. Is it true or is it false? It's true, right? That's it. So this is how you do an existence test. This is very, very easy and compact. Now, what you're going to tell me is, yes, but what if we don't use EQ and we put an equal sign instead? No big deal, do it. In fact, many engines will automatically detect that they can optimize. So if they see an equal sign and they know that there's only one item on the left and only one on the right, they will automatically rewrite it as EQ. So in fact, and now recently we started putting this optimization in RumbleDB as well. So you really don't need to worry too much between equal and EQ. Both of them will work. You just need to be aware that EQ is normally for single items and the actual signs are for sequences. Yes? Then we go for a break.
Does the equal sign have some other special use case that makes sense for you? Because right now, just using it to check for existence
doesn't make that much sense to me. Like, why would we want to give the equal sign superpower and not just have an in statement or something? So here, this is basically a W3C standard, right? So this is part of the standards X query. The main reason, the way that these standards are built is that there is typically, in addition to the specification, there is a use cases document. And in the use cases, it turns out that many people who were querying data, and probably from the publishing industry, actually had many cases where they need to test whether a specific value appears in a list, right? So this is the reason why it was made so in the syntax, just because there was a use case and there were several people who had really a justification for that use case. What if we hadn't done that? We just would have had more verbose syntax, right? We would just have written it in a different way that might have been longer. So really, this is use case driven, and it is that way because some people needed it or need that actually quite often. And actually, you might see in practice that actually happens more often than you would think when you query a data set. Yeah. Okay. Let's go for a break. Who wants to go for a break? Of course, you want to go for a break. All right. So 15 minutes, and I'll see you at 3:15 for the continuation. Thank you.